SYBSCच्या ह्या लेक्चरमध्ये आपण रँक नलिटी थेरम अभ्यास करणार आहे. सपोज T, V and W are real vector spaces. Let V and W are real vector spaces. V and W are real vector spaces. Real vector spaces. T from V to W be a linear transformation. तर इथं व्ही आणि डब्ल्यू हे रिअल वेक्टर स्पेसेस आहेत आणि टी फ्रॉम व्ही टू डब्ल्यू हा लिनियर ट्रान्सफॉर्मेशन आहे. आपल्याला माहित आहे की लिनियर ट्रान्सफॉर्मेशन, व्हॉट इज ए लिनियर ट्रान्सफॉर्मेशन? हियर लिनियर ट्रान्सफॉर्मेशन इज अ फंक्शन from a vector space V to vector space W satisfying these properties. Number one property, T of V1 plus V2 is equal to T of V1 plus T of V2, and T of alpha V is equal to alpha T of V. Here V and W are real vector spaces and T from V to W is a linear transformation. Is a linear transformation. Then we know what is the kernel of T. We have studied the kernel of T. The kernel of T is the set subspace of phi. Kernel of T is the set of phi belong to phi such that T of phi is equal to 0 element of W. We know that the kernel of T is the set of phi belong to phi such that T of phi is equal to 0 element of W. This is the kernel of T. Now the kernel of T is the subspace of phi. We know that kernel of T is the subspace of phi, and it's the dimensions of kernel of T is called as the nullity of T. The kernel of T is a subspace of phi. We know what is the subspace. Subspace means it is a subset of a vector space which is itself a vector space for the addition and scalar multiplication as defined as those defined on V. The kernel of T is the subspace of V. The dimensions of kernel of T, the dimensions of kernel of T is called as the nullity of T. Is called the nullity of T. Here now, what is the image of T? We know the image of T. It is the set of small vector W belong to capital W such that for each W belong to for each W there exists some phi belong to V such that W is equal to T of V. Now the image of T, we know all this. The image of T is the set W belong to W such that there exists phi belong to phi such that T of V, T of V is equal to W. T of V is equal to W. See here, thus the image of T is the set of W belong to capital W, such that there exists V belong to V, such that T of V is equal to W. Means the image of T is the set of T of small v, such that V belong to V. The image of T is the so we know that the image of T, the image of T, the image of T is a subspace, is a subspace of W, subspace of W, W. Now, the image of T is a subspace of W. The dimensions of image of T, the dimensions of image of T, image of T is called as the rank of T, the rank of T, the rank of T. Means of here sub image of T is the set of V belong to V, is the set image of the image of T is the set of W belong to W, such that there exists some V belong to V, such that T of V is equal to W. Means the image of T is the image of T is the set of T of V, such that V belong to V. The image of T is the set of image points of T. Image if T is an onto function, then obviously image of T is W. But if T is not an onto function, then image of T is a proper subset of W, and the previous theorem state that the image of T is the subspace of W. The dimensions of image of T is called as the rank of T. Now we have to study the rank nullity theorem. The rank nullity theorem nullity theorem the rank nullity theorem, let V and W be real vector spaces, be real vector spaces T from V to W is a linear transformation, is a linear transformation. Then the rank of T, the rank of T, the nullity of the rank, the nullity of T plus the rank of T plus the rank of T is equal to dimensions of V. Now see here, This is a very famous theorem in the linear algebra. See here, what is the statement of the theorem? Suppose V and W are real vector spaces. Means V and W are vector spaces over the set of real number. And T from V to W is a linear transformation. Then the theorem states that the nullity of T plus the rank of T is equal to dimensions of V. We know what is the nullity of T. The nullity of T means dimensions of kernel of T, and the rank of T means the dimensions of image space of T, and V is a codomain space. Therefore, the dimensions of kernel plus the dimensions of image space is equal to dimensions of codomain space V. This is the rank nullity theorem. Let us prove this. Proof of the rank nullity theorem. Proof. Let V and W be real vector spaces. Let V and W be real vector spaces. Real vector spaces. T from V to W be a linear transformation. Be a linear transformation later dimensions of phi is equal to n. Let dimensions of phi is equal to n. Now suppose T from V to W be defined as as T of V is equal to 0 of W. T from V to W be defined as T of V is equal to 0 of W. Then the kernel of T, in this case the kernel of T is the whole set V, means the vector space V. In this case in this case the kernel of T is equal to phi. Therefore, the nullity of T is equal to n. That is equal to the dimensions of phi. The dimensions of phi. Dimensions of phi is equal to n. Now the image space, here the image space the image space here is equal to 0 of W. Therefore the rank of T is equal to dimensions of image space. The dimensions of image space is equal to 0. Therefore, now n plus 0 is equal to n. Therefore, the nullity of t, n is equal to the nullity of t. The nullity of t now the rank of t is equal to dimensions of image space plus the dimensions of the rank of t. The rank of t is equal to n, means the dimensions of v. Dimensions of v. Therefore, when t is a zero linear transformation, that is t of v is equal to 0 element of w for all v belong to v, then the rank nullity theorem is verified here. Here n plus 0 is equal to n is equal to the rank of t, 0 is equal to the n is equal to the nullity of t, 0 is equal to rank of t, the rank of t, and is equal to dimensions of v. Now suppose in general case, let us prove this theorem. Let t of v is not equal to 0 of w for all v belong to v. For all v belong to v. Now see here, that is the kernel of t is not the whole space. Now t from v to w is a linear transformation. Is a linear transformation. The kernel of t, as we know, the kernel of t is the set of v belong to v such that t of v is equal to 0 of w. Now we know that the kernel of t is the subspace of v. The kernel of t is a subspace of v. Subspace of v. Let its a dimension is equal to k. Its a dimensions is equal to k. Means we know that kernel of t is the subspace of v, and suppose its dimension is equal to v. Let b dash is equal to v1. Let b dash is equal to v1, v2 dash vk be a basis of kernel of t. Be a basis of kernel of t. Basis of kernel of t. Later here t from v to w is a linear transformation, and we know that the kernel of t is the set of v belong to capital V, so that t of v is equal to 0 element of w. The kernel of t is the subspace of v. Let its dimension is equal to k, and therefore let b dash be a basis of k, kernel of t, and b dash contains k different elements v1, v2 dash vk be a basis of t. Now since kernel of T is a subspace of phi and B dash is a basis of kernel of T, it is we can extend this basis B dash to a basis of phi. We can let us extend the basis B dash the basis B dash of kernel of T to a basis B of phi. Let to a basis B of phi. Let B is equal to phi1 comma v2 dash 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 comma vk comma vk plus 1 comma vk plus 2 dash 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 comma vn be a basis of phi. Be a basis of phi. Here B is an extension of the basis B dash, where B dash is the basis of kernel of T. B dash contains k different vector v1, v2, vk. Here we extended B dash to a basis B of phi, and B has n elements v1, v2 dash 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 vk, vk plus 1, vk plus 2, vn. Now we prove that we prove that that the set vk plus 1 comma vk plus 2 dash 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 comma vn is a basis of image of T. Is a basis of image of T. Of image of T. See here, image of T is here we prove that the set phi k plus 1 comma phi k plus 2 comma dash 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 comma vn is a basis of image of T. We prove that for this we here prove two things. First, we prove that the set vk plus 1 comma vk plus 2 dash 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 comma vn is a linear independent set, and it span the image T. It span the space image T. For the let us prove that prove that the set let us prove that the set T of vk plus 1 T of vk plus 2 dash 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 T of vn is a basis of image of T space, image space of T, image of T. See here we prove that the set here this set T of vk plus 1 comma T of vk plus 2 dash dash comma T of vn is the basis of image of T. See here T from V to W is a linear transformation. Now the vectors T of vk plus 1, T of vk plus 2, T of vn all belongs to W, and we prove that this set is a basis set of image of T, And for that we prove that this set is linear independent. We prove that this the above set B double dash is equal to T of Pk plus 1 comma T of Pk plus 2 dash 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 comma T of Pn is linear independent. Dependent. See here, we prove that B double dash means the set of vectors T of Pk plus 1, T of Pk plus 2, T of Pn. This set is linear independent. Now see here proof of this. Let alpha k plus 1, alpha k plus 2, dash 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 alpha n belong to R be such that T of alpha k plus 1, T of k plus 1, T of Pk plus 1 plus alpha k plus 2, alpha suffix k plus 2, T of P suffix k plus 2 plus dash 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 plus alpha suffix n T of Pn is equal to 0 element of W. See here the vectors T of Pk plus 1, T of Pk plus 2 and T of Pn all lies in W, and therefore suppose in order to prove that this set is linear independent, the set B double dash, that is the set T of Pk plus 1, T of Pk plus 2, T of Pn is linear independent. We see here, we assume that suppose alpha k plus 1 comma alpha k plus 2 dash dash alpha n belong to R be such that alpha k plus 1 times T of Pk plus 1 plus alpha k plus 2 into T of Pk plus 2 plus dash alpha n T of Pn is equal to 0 of W. Now in order to prove that this set is B double dash is linear independent, we prove that this happens only when alpha k plus 1, alpha k plus 2 and alpha n all are 0. Now since T is linear transformation, alpha k plus 1 T of Pk plus 1 can be written as T of alpha k plus 1 Pk plus 1. Because T is a linear transformation, T of alpha is a scalar and therefore T of alpha k plus 1 Vk plus 1 is equal to alpha k plus 1 on into T of Pk plus 1 plus T of alpha k plus 2 Pk plus 2 plus dash 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 plus T of alpha n Pn is equal to 0 of W, 0 element of W. Now this can be written as T of alpha k plus 1 Pk plus 1 plus alpha k plus 2 Pk plus 2 plus alpha n Pn is equal to 0 of W. Since T is a linear transformation, the previous statement is this statement. Therefore, T of alpha k plus 1 Vk plus 1 alpha k plus 2 Vk plus 2 plus dash dash alpha n Vn is equal to 0 of W. Therefore, the vector alpha k plus 1 Vk plus 1 plus alpha k plus 2 Vk plus 2 plus dash 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 alpha n Vn belong to kernel of T. Therefore, the vector now this vector alpha k plus 1 Vk plus 1 plus alpha k plus 2 Vk plus 2 plus dash dash s plus alpha n Vn is associated with 0 element of W by T, and therefore this vector alpha k plus 1 Vk plus 1 plus alpha k plus 2 Vk plus 2 plus dash dash alpha n suffix Vn belong to kernel of T, and therefore there exists alpha 1, alpha 2, alpha k belong to R such that alpha k plus 1 there exists a minus alpha 1, minus alpha 2, minus alpha k belong to R such that alpha k plus 1 Vk plus 1 plus alpha k plus 2 Vk plus 2 plus dash 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 plus alpha n Vn is equal to minus alpha 1 P1 minus alpha 2 V2 plus dash 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 minus plus minus alpha n Vn. Therefore alpha 1 V1 plus alpha 2 V2 plus dash 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 plus alpha n Vn plus alpha not here there exists alpha 1, alpha 2, alpha k belong to R so that alpha k plus 1 Vk plus 1 alpha k plus 2 Vk plus 2 plus dash dash alpha n Vn is equal to minus alpha 1 Vn minus alpha 2 minus alpha k Vk, not n. Therefore alpha 1 V1 plus alpha 2 V2 plus alpha k Vk plus alpha k plus 1 Vk plus 1 plus dash 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 plus alpha